Hello viewers, this video will do Cambridge A-Level Further Maths Pure 2 paper. The syllabus code is 9231 and this is variant 3 from the May-June 2025 series. We will attempt question 7 in this video. The previous questions have been uploaded into the same playlist. Question 7 is given this differential equation and some boundary conditions, and they want us to find the answer or the solution in an exact form. First of all, we can try and recognize that this is a linear first order differential equation, and a linear differential first order will present in the form. This is the form that a linear first order differential equation presents as. You have the derivative add together with a function multiplied by y, or the dependent variable, equals to another function in terms of x. So the solution to this type of linear first order differential equation, um, first of all, we need to use something we call what we call the integrating factor mu of x, which is e to the power of the integral of px, which is whatever function is multiplied together with the y, or the dependent variable. In this case, the px is this entire function of the fraction here, and so or let me just finish proving this first. So to solve this this form of differential equation, we multiply the entire differential equation with the integrating factor on both sides. Once you multiply it, you can go ahead and expand the left hand side, or we'll do some manipulation on the left hand side, so that after you expand it, it looks something like this. And this is actually a result of the not chain rule, the product rule, where you take the derivative of the integrating factor multiplied by the dependent variable. So since mu and y, they are both functions of x, so we need to use the product rule to differentiate this. First, we leave the mu x function and we differentiate y. So y is a function of, it's just an arbitrary function of x, so we just write dy dx. Then we add together the derivative of mu x, which we have set to be e to the power of something. So differentiate exponential function, you just rewrite the exponential function and multiplied by whatever the inside function is, which in this case, the inside function is the integral of px, for which when we differentiate the integral of px, we just get back px, because the differential and integral, they are opposites of each other. So this I'll write this entire thing as the integrating factor, so that it's clearer to see. And then of course we leave y, we do not differentiate y. So this is the product rule, and you can see that this is true. So the entire left hand side, you can reduce it to the derivative of the mu x multiplied by y. And we get this relation where the derivative of mu xy equals to mu x multiplied by qx, the original equation. Okay, this is the original differential equation. We reduce it to this form. So uh, after we reduce it to this form, is the solution should be simple, where we can integrate both sides and we can find the solution there. Okay, so let's deal with our specific differential equation here, where our px, where we have already established that this is the fraction, right? 2x plus 6 divided by x squared, 6x plus 5. And therefore, our integrating factor, to do the integration up there, what I'll do is I'll probably use a u substitution, where let u is equal to the bottom function, because um, if you can notice that the top function is basically the derivative of the bottom function. So what we can do is just take the derivative in terms of x, and we get 2x plus 6 dx. So this 2x plus 6 dx is up here, so we can replace that thing with just du. So I rewrite here mu x equals to e to the power of the integral of du And then the bottom is what we have set as u. So it's a du over u, and you just get e to the power, or I mean, the integral of 1 over u in terms of u, that's ln of u, natural log. So u we have set as the quadratic expression, so I'll just rewrite like that. So this is our um, integrating factor, but we can go ahead and simplify this even further because e and the ln can cancel, and we're just left with the quadratic. Am I missing? I'm missing. I've missed out the negative everywhere, right? I missed out the negative here, here, and then here also, and here. So the negative, what I should do is, before I cancel out, I will have a power of -1 in the entire quadratic expression. So it'll be 1 over x squared plus 6x plus 5 is the reciprocal of that, be due to the power of -1. So after which, okay, we have gotten the integrating factor mu x. Following back the steps I've outlined before, we multiply both sides of the equation by this integrating factor, which, okay, I'll multiply now. After multiplying, I should be able to get this expression, for which we know the left-hand side reduces, or we have proven the left-hand side reduces to the derivative of the integrating factor, which is, again, our reciprocal of the um, quadratic expression multiplied by the dependent variable y. And on the on the right-hand side, we just leave it because we do nothing there. And from here, what we do is we just integrate with respect to the respective differentials on both sides, right? So on the left hand side, we integrate with respect to this expression, and on the right hand side, we integrate with respect to x. And here I'll go ahead and complete the square for this quadratic expression on the bottom, because that is one of the integration techniques, right? So I have x plus 3 squared and minus 4. The 4 on the top, I'll take it out of the integrand. So like that, and this 4 I'll make it into a 2 squared so that we can do some integration tricks. If we notice here, this integrand is in the form of this one, x squared minus a squared. Our x squared in this case, I mean our x in this case is x plus 3, and the a squared is 2. So what we can do is we can directly, or we can use this formula to um, to complete our integration. So this, I mean the x becomes x plus 3 and a becomes 2. So we have 4 divided by 2 times 2, then natural log of x plus 3 minus 2 and x plus 3 plus 2. And on the left hand side, what we have, the integral and the differential cancels out each other. We'll have just the whatever expression we had before. Okay, so we go ahead and simplify a bit further. Okay, so once we've completed the integration, we will add the arbitrary constant down here. We didn't add the arbitrary constant before using the integrating factor because that was just a dummy integration. So up there it didn't matter, but this is including the final answer, so it does matter down here where we add the constant. So the initial conditions or the boundary conditions given us y0 is at 0, right? So given that y of 0 is 0, the whole left hand side reduces to 0, and on the right hand side we have ln 1 over 5 plus c. So c is the negative ln 1 over 5, and therefore our final solution, y will be ln x plus 1 x plus 5 minus ln 1 over 5, And if you want to get an um explicit equation in y of x, right? Y as a function of x, you can just multiply both sides by the quadratic expression down there. Okay, so yep, this should be the final answer in an exact form. So we leave the constant as the natural log, and yeah, that's how you solve the linear first order ODE. Okay, thank you for watching.